So let's do a shear and bending moment example. We've got a 20-foot long beam with a point load at mid-span, a 100-pound per foot load along its length. Again, that 800 pounds right in the middle. Find our reactions, RAY and RBY. There would be an RAX, but we can safely assume that it's 0 since there's no forces applied in the X direction. So there's going to be no X reaction there. There's not going to be any normal force in this beam. Summing moments about B will give me RAY. RAY is 1,400 pounds. And now, I could sum forces in the Y, but I can recognize the symmetry. I got 800 pounds in the middle. I've got 100 pounds per foot over the entire length. That's 1,400. That one's also 1,400. As a matter of fact, since this was all symmetrical, I really didn't even need to do the moment equation. I could have just said that 20 times 100 is 2,000 plus 800 is 2,800 divided by 2, half each side, 1,400, because it's loaded symmetrically and the geometry is symmetric. That happens a lot. It's a special case for sure, but it happens a lot. Recognizing symmetry really can speed you up in statics. How many free body diagrams are we going to need for our functions? We're going to have 2. We're going to have one in the first 10 feet, one in the second 10 feet, because of that 800-pound load. So let's look at the first one. This is the free body diagram that is valid between A and C. So my domain is going to be x1 is going to be between 0 and 10. We're going to come up with functions in terms of x. So I have to know what values of x are applicable. I can't plug into these equations I get. I can't plug in 15 feet because it doesn't work. It's not in the applicable domain. So I've got here my free body, cut at some distance x1, whether it's x1 is like 1 foot or 9 feet, doesn't matter, right? Because this free body is valid for that. So I've got a 1,400-pound reaction. Here I have a 100 pounds per foot distributed load acting over x1 length. So the resultant is going to be 100x1. It's acting at a distance from the cut end at half of x1. And I draw my shear pointing down, my moment counterclockwise because the cut is on the right. And I sum forces for my shear. And I get my shear is going to be equal to, V1 is equal to minus 100x plus 1,400 pounds. Okay, minus 100x1 plus 1,400 pounds minus V1 equals 0. You can see how this equation is built. And my moment equation is done very similarly. So I've got about the cut. Counterclockwise positive, I have M1. Then I have 100x1 times the distance of x1 over 2, so 100x1 times x1 over 2, and then that's a positive moment. This 1,400 pounds over here is a clockwise moment, so it goes in as negative. 1,400 pounds acting at a distance of x1 is equal to 0. Clean that up a little bit, and I get that m1 is equal to minus 50 x1 squared plus 1,400 x1. If you're savvy, you might be recognizing that the moment is the integral of the shear, and that's true. We usually recognize that, and like I said, when you get to these graphical methods, that becomes very important to recognize. But don't think you're going to be using your calculus to integrate your shear to get your moment, because sometimes evaluating that constant of integration can be quite tricky. It's much better just to use the equilibrium equations that you have learned here in the statics course. So then I'm going to evaluate those functions at their start and end regions, so at 0 feet and at 10 feet. So at 0, the shear is 1,400. And at x1, equal to 10 feet, I have V1 is equal to 400 pounds. Looking at my equation, it's obviously just going to be a negatively sloped line from 1,400 down to 400. And then my moment is this equation that we did. At x1 equals 0, the moment is 0 because x1 is in both terms. And at x1 is equal to 10 feet, my moment is 9,000 foot-pounds positive. That's a parabola concave down because of the minus 500x squared. So far we have this. I have 1,400 down to 400, negatively sloped line, 0 up to 9,000, concave down parabola. Let's look at the second region. This is going to be between C and B, so the right-hand side over here. So now we have x's that are, x2 will be valid between 10 feet and 20 feet. So anything between C and B. The difference, this 800-pound force, right? It's also a little bit more complicated because now I have x2 is this distance from A over, right? So if I'm starting to calculate moments about the cut, I'm going to need to know this distance here, and this distance is x2 minus 10. So that's where this x2 minus 10 comes from. Let's develop our equation. So shear, we use some forces in the y. We get minus 100x2 plus 600 pounds. Pretty straightforward. And then our sum of moments about the cut, we have m2, and then I have plus 100x2 times x2 over 2. That's the resultant of the distributed load. Then I have minus 1400 times x2, so that's the reaction. And then this point load here is being added into the mix. It's going to be 800 pounds at a distance of x2 minus 10 equal to 0. And after some more finagling and simplification, I get minus 50x2 squared plus 600x2 plus 8,000 foot-pounds. So again, this is the moment is the integral of the shear, but this is one of those spots where I'm definitely telling you, like, you would not have thought to use that constant of integration. So just solving the equation of equilibrium outright is really the way to go. Again, evaluate at the start and end points. So at 10 feet, because that's our start point, V2 is equal to minus 400 pounds, and at x2 is equal to 20 feet, V2 is equal to minus 1,400 pounds. And that's also a negatively sloped line. Matter of fact, it's got the same slope. The slope, by the way, of the shear, if you have a distributed load, is going to be the value of the distributed load at that point, because the load is the derivative of the shear. Here's my moment function. Evaluate that at 10 feet and at 20, and I get these two values. Again, parabola. Negative means concave pointing down. So then my complete graph is that.